friends, and welcome to the introduction to linear regression. So in this lesson, we're going to get a light theoretical background, perhaps, we'll say. Anyway, we're going to get behind the idea of linear regression before we actually tackle the concept with Python and the Scikit learning library, okay? So now let's get into that background. Linear regression. So the entire idea all started way back in the 1800s, believe it or not. There was a man called Francis Galton, and Galton was working on relationships between parents and their children. Especially, he was exploring the relationship between the height of the fathers and their sons. What he discovered was that a man's son tended to be roughly as tall as his father. However, Galton's breakthrough was at his son's pinnacle, tending to be closer to the overall average height of all people. So let me show you, and I'll just make an example of this. Okay, so LeBron James, very tall. Well, of course, you have to be as famous as he is for playing in the NBA. Anyway, without getting into any controversial figures, let's say, just for the sake of argument and mathematics, that he is 6 feet 7.5 inches, or 2.06 meters tall. Now, if LeBron has a son, as it's known, he will also be quite tall. But LeBron is so abnormal in his height that it is very likely that his son is not going to be as tall as LeBron. And it turns out that this is the case. So LeBron James' son is quite tall. He's 5 feet 8 inches. Not quite as tall as his dad, though, who is 6 feet 7.5 inches. Now, Galton called this phenomenon regression. Okay, you with me? Just like a father's son's heights tend to regress or slide to the mean or average height of everyone else. Okay, so let's go ahead and begin to plot out the example so that you can see. We'll calculate a regression with just 2 data points, which is the simplest possible example. Right? So here we have 2 data points, x equals 2, y equals 4. And so this is one data point. X equals 5, y equals 10. This is our other data point. These 2 little black dots. Now, the only thing we're going to try to do in calculating our regression line is to draw a line as close to each point as possible for the classical linear regression, or least squares method. So you measure proximity only in its up and down movement. Now we have a perfect line here because we only had 2 points. But wouldn't it be great if we could apply the same concept to the graph with just more than 2 data points? So by doing this, we can take the height of multiple men and their sons and then perhaps predict for a guy how tall his son is going to be even long before he has one, right? So this is the idea behind supervised learning. We're going to have a bunch of labeled data points, create a model. So in this case, we're going to use regression theory and try to take unlabeled data, such as a father's height, and then spit back out some labeled data. So we'll have a group of labeled data points forming a pattern. And in this case, we'll theoretically try to retrieve unlabeled data, such as regression and father's head, and return the labeled data to our estimate of his son's height. Now, with linear regression, our goal is to minimize the vertical distance between all data points and our line. Therefore, when we determine the best line, we try to minimize the distance between all points and their distance from our line. There are actually many different ways to minimize this, some of errors, some of absolute errors, and so forth and so on. However, the general purpose of all of these methods is to minimize the distance between your line and the remaining data points. Yes? For example, one of the most popular methods we have that I just described is the least squares method. Here are a few blue data points along the X and Y axis. So now we want to fit a linear regression line. So the question then becomes, how do we decide which line is the best fitting one? Well, we can go ahead and use the least squares method that we discussed. This method is fit by minimizing the sum of the squares of the residuals. The residuals for an observation is a difference between the observation of the y value and the fitted line. Follow? So in this image, the residuals are marked by the red line, the difference between true data point in blue and your fitted model line, black baseline. All right, my dear friends, to recap, we have just learned the theory part of our linear regression. So I want to see you in the next lesson, and we'll have some fun with that. Well, hello, dear friends, and welcome to Fun with Linear Regression. Just playing, but no, it will be fun. Anyway, linear regression with Python, okay? So we've already learned the theory behind linear regression, so let's go ahead and use scikit-learn so that we can implement our own linear regression models. So we'll start by working with a housing data set, and this tries to build a model for predicting house prices based on available properties. So as linear regression is our first machine learning algorithm, we're going to be working with some artificially generated data sets. So we'll continue to use real and more complex data sets later, but you don't want to focus too much on the cleanliness or the data right now. We're just going to focus on the process, and we'll get true later, all right? So right now, we just want to get the basis of how we create this model. Okay, so let's go ahead and jump into the notebook and get started. All right, now before starting up the notebook, a little public service announcement here. With this notebook, the CSV file that we're going to work on must be located in the same directory. You remember this, right? Otherwise, you will get an error while you're importing data. All right, so double check that. Let's go ahead and get started. First thing is, we have to import, and what's going to happen here is we're going to say import pandas as PD, and we're going to say import NumPy as NP, and then we're going to need to import our visualization libraries. I'm going to say import Matplotlib.pyplot as PLT and import Seaborn as SNS. And then in order to see these visualizations in the notebook, I'll need to specify %sign matplotlib inline. Okay, so let's go ahead and take a look at our data. So I'm going to create a data frame named df and say pd.read_CSV and call predict_house_price. And let's go ahead and check the head of the data frame. We have a total of 7 columns in this data frame. We have rows representing a particular house in here. The last row is the price column, and the house is sold at a specific price. Good, so these other columns represent statistics for the city or region where the home is located, such as, let's see what we've got, the city's population, the average number of bedrooms for houses in that area, number of rooms on average for other houses in that area, average house age for houses, and people's average income. Okay, so these are all good. But again, these first few rows that start with the mean area correspond to the location or the city of that house. And remember, of course, this data is just, for example, it's artificially created, so any significant numbers after the decimal point, they're usually going to have that much accuracy. Okay, so dear friends, now we can go ahead and examine this data a little bit. So what I always recommend you do is take a good look at the info method. And this is right here on your data frame. And this will give you information about the total number of columns and the total number of entries. Now, besides giving a few clues or statements about what types of objects there are in the data frame, the other thing that I would also recommend you do is call the describe method, and it gives you the ability to get a quick account. So this method gives us statistical information, such as the mean, minimum, and maximum value, standard deviation, etc., the numerical columns. So notice here the address column, well, it's not available because that was a string value. Another quick note here, if you ever need to reference the column names, well, you can just say df.columns and return back a list of the column names. So let's go ahead and do some simple plots to examine our data. One very simple plot you can do if the data isn't very large is Seaborn pair plots. And then you can just pass the entire data frame. And this will automatically generate not only histograms of all the columns, but also correlate scatter plots. And this is what that looks like. You can see the histograms that everything seems to be more or less normally distributed except for the average number of bedrooms column. And you'll notice that the average number of bedrooms is divided into 2, 3, 4, 5, and 6. And there's some noise around here, but usually can't have 2.5 bedrooms. So that's why this kind of behavior occurs. Okay, so let's go ahead and look at the distribution of one of the columns. Now, you'll most likely want to check the distribution of your target column, or what you're trying to predict. So in this case, we're trying to predict the price of the house. So let's go ahead and check out the distribution of the price. Okay, the average price seems to fall somewhere between 1 and 1.5 million, around 1 million. And everything seems to be distributed from there pretty normally. Now, of course, this won't always be the case when it comes to pricing or other target variables. They might not be distributed normally, but that's a nice case because we're not really trying to clear this data, okay? Oh, and the other thing that you might want to do for a data set is to make a heat map of the correlation between each of the columns. So you can say df.corr, and this will give you a correlation matrix. So let me just go in here and show you what that looks like. df.corr, and this is the correlation between all the columns. And then you can plot that out as a heat map just by passing that in through the SNS.heatmap. And then here we can see that in general, you'll see the diagonal of the exact correlation, and that's meaningful because each column itself has to be perfectly correlated, and then you will also be able to see some information based on other columns. So right now we get a lot of gray and low correlation amounts, and you can actually see this numerically just by saying annote equals true. All right, so let's go ahead now and shift our focus to actually using the scikit-learn and training a linear regression model. The first thing you're going to want to do is split the data into an X array with the properties to train, a Y array with a target variable. And in this case, the price column we are trying to predict will continue, and the address column will be thrown out because right now it only has text information that the linear regression model won't be able to use. Okay, so I'm going to go ahead and say df.columns to grab my column names, and then I will set x equal to df, and then pass in a list of the column names, and I can just go ahead and actually grab this from here and paste it. Or I'm going to say x equal df.drop, and then write the columns that we want to drop in brackets. So the address variable that we will not use in our price and model, which is our main target variable, we have to set the axis parameter to 1 because we want our columns to drop. And then y is going to meet my target variable. So what I'm trying to predict in this case is the price column. Right, so now that we have x and y data, our next step is to do a train test split. So we want to split our data into a training set for the model and then a testing set as well so that we can test our model once it has been trained. So we're going to go ahead and use scikit-learn to do this. So scikit-learn comes with a train test split function, and you can just grab it by saying from sklearn .model_selection, and then you want to do import train test split. So it's a Shift tab in Jupyter Notebook to read the documentation string for it. So you can scroll down and see a good example here where you say x train, x test, y train, y test is equal to train test split, x, y, test size, and then a random state that we can add. All right, so we'll go ahead and copy this line. Copy it, and I'm just going to paste it here and put it all on one line. All right, my dear friends, let's go ahead and set our test size 0.4 and our random state 101. All right, so let me try to explain what happened here. This is actually using tuple and packaging to get your training set and your testing set. And you're going to have your X train and your Y train. And then you're going to have your X test and your Y test, right? Okay, so then in the train test split function, you can pass in your X data, your Y data, and you optionally choose a test size as well. And this test size, well, it's only a percentage of your data set that you want allocated to the test size, right? Okay. So in this case, we are going to go and allocate 40% for test size. It's also very common to make it 30 or 0.3% most of the time. So then this random underscore state equals 101. You can pass in an optional number here if you want, but essentially it guarantees that a certain number of random splits will occur in your data. Since this train test split will happen randomly, to make sure that your random split is the same as my random split, just go ahead and specify random underscore state as equal to 101. That way we'll get the same random splits. You follow, right? Otherwise, your results might not match exactly mine, and somebody's going to be wondering what's what. Anyway, it will still be true. You just won't have the exact same numbers as your result. Okay, so now that we have our training and testing data, let's go ahead and run this. So we have to build and train the model, yeah? So the next step is, say, from sklearn dots, and linear regression is found under the linear underscore model family. So we say linear, and you can use the tab to complete this import automatically. And we want the linear regression model. Okay, so once it's imported, the linear regression model will go ahead with this, instantiate it, and here we have an instance of linear regression model. So I'm going to go ahead and make a variable called lm equals, and then say linear regression, and instantiate some, basically creating a linear regression object. Now I'm just going to say lm dots, click tab, and we'll check out all the available methods. If there are all these available methods in my model, then the first thing I'm going to want to do is use the appropriate ones to train or fit my model or training data. So I'm going to choose fit method. So if we look at the shift tab, well, this method will take an X and Y and so on and fits the linear model. So in this case, I just want to fit my model to my training data. So instead of just passing in X and Y, what I'm going to do is say X-train, Y-train. And I know that I get an output telling me the linear regression model was trained. Now notice also that I didn't set this equal to any other variable object. This already has an effect on the object itself. So I don't mean to say lm equals lm.fit. You can just say lm.fit. Okay, so now the next step is to evaluate our model by looking at its coefficients and then seeing how we can interpret them. Let's go ahead and print the intercepts. I can grab the intercept by calling for my model, lm, and then saying intercept, and then underscore at the end. Or you can just use tab autocomplete. All right, so the next thing you can check are the coefficients, and the coefficients will be related to each feature in our data set. You can grab the coefficients by saying lm.coef underscore, and this will return the coefficients for each feature. Okay? Okay. Now, to organize this a little better, let's go ahead and create a data frame based on these coefficients. So each of these coefficients relates to the columns in X or X-train. So just go out and check that these are the same columns, X and X-train. So what I'm going to do is to go in here and create a data frame off of these. So I'm going to say PD data frame, pass in the coefficients as my data, pass in the columns as my index, and I'm going to go in and say columns is equal to coef. All right, so let's go ahead and set this equal to CDF for coefficient data frame. And then we'll call this CDF now. All right, so here we have a coefficient for each feature. And perhaps if you want a more mathematical reasoning behind these coefficients, just ask to read how they work, and I'll briefly explain how to interpret these coefficients. But basically, what does this mean? Well, if we look at the former, keeping all the other features constant, a 1 unit increase in average area income is associated with an increase in price of $21.52. And then for the latter, we could say something like an increase in mean area house age of 1 unit is associated with an increase of $164,883. And you'll be able to do a similar analysis for each of these features and their coefficients. Now, you might be wondering if this really makes sense. Probably not, because this is indeed artificially generated data. But if you do want to do a real data analysis, you can actually repeat this project on the Boston data set. So this is the same dwelling type data. It, however, happens to be actually true. You can actually find it from research done in the 1970s, and it is in this Scikit Learn. Let me just go ahead and show you how to grab the Boston data set. So what you can do is call from sklearn.dataset, import load underscore Boston. Now there's a link in your notebook for the documentation on this data frame. But basically what you do is say Boston is equal to load underscore Boston. And then you call it, you actually call that function load Boston. And then if you check it out, what Boston is essentially a dictionary with a whole lot of information in it. You can check out the description of the data set by saying Boston, DECR. And this will print out the Boston houses price data set. So this is real, actual housing data. So if you want to do a similar analysis for house price data in a real data set, you can repeat the analysis of the lesson here that we're doing. Because if you look at it, this data is fairly old. And then if you want to capture the data itself, you can just say the data, and here you see your data. And then you can also take feature names here, which are essentially columns or data frames, and then capture the target as well. And these are all the target prices in thousands. All right, my friends, you see what we're looking at. So let me ask you that if these coefficients were negative, would you say that for every increase in the unit, you would get a downsize of the price of the house? Well, we'll finish the first part of our analysis here. And then in the second part, we'll discuss getting predictions from our model. But before we get to that second part, let's just step back for a second, take a quick look at everything that we did. So first, we had to actually grab that data using Pandas and the pd.read CSV. We did some exploratory data analysis to get familiar, but didn't want to focus too much on that as it's synthetic data. And then we separated our data into X and Y, where X is features, Y is what we're trying to predict. We said from sklearn.model_selection, import train test split. We went ahead and split our data by specifying a test size and also specifying a random state. And your results were the same as shown in this video, yes? So then we said from sklearn.linearModel, import the actual model linear regression. And we created a linear regression object, basically an instantiation of a linear regression model. Then we fit this model to the training set and explored the intercept and the coefficient. Now, if you do want a bigger breakdown of how to interpret these coefficients, you can always refer to the Jupyter notebook for this lesson. And then we simply formatted the coefficients into a nice data frame so that we can read it by a human. All right, and then at the end, we showed you how you can access a real data set from Scikit-learn. To grab this data set, we said from sklearn.datasets, import load Boston. And in case you want to repeat the sort of analysis on a real data set, you can use this. All right, so that gets us up to here, but we're not quite finished yet. So in part 2, we'll discuss how we actually grab predictions from our model based off of that test set. All right, thanks very much for sticking to it and getting this far. I look forward to seeing you in the next lesson. Hello, dear friends. Welcome back. So this is the beginning of the second part of the linear regression lesson of using Python. So we're going to focus now on getting predictions from our model. So we'll go ahead and Go back to the notebook that we started last time, and here I am in Jupyter Notebook. You might recognize it, and we're able to create our latest model and fit the model to our training set. So now we want to grab predictions from our test set. So what you can do is say predictions is equal to lm dot. And then we're going to call the predict method. And the predict method, pass in the x, just the features. So in this case, we want to pass in features that the models haven't seen before. So we want to pass in x underscore test, which is the testing set, and just the features. Then we can go ahead and then check the predictions. And if we just look at the array of predictions, here's a dot, dot, dot. These are the estimated prices for the house. However, since we did train test split, we know that the y-test includes the correct prices for the house. And we want to know how far the predictions are from the test prices to real prices, right? So there is a quick way to analyze this visually just by simply making a scatter plot. So you can say something like plt.scatter from Matplotlib and compare y-test with your estimates. And if they line up something like this, you're doing a pretty good job. So this means that a perfectly straight line will be completely accurate in its predictions, right? So getting a little out of the straight line is actually a very good job. So let's go ahead and actually create a histogram of the distribution of our residuals. So I'm going to say SNSDistPlot. And with the residuals, remember these are going to be the difference between the values predicted by the y-test. So I'm just going to go ahead and pass in y-test minus predictions. And we can go ahead and create a plot like this. So now this is going to be a histogram of the residuals, right? So notice that our remains here appear to be scattered normally, which is a very good sign. If you distributed the remains normally, it means that your model is the right choice for the data. So of course, the converse is true. If this is not normally distributed and you have some sort of weird behavior going on here, you might want to go back to your data and check to see if a linear regression model is the right choice for your data set. There are others. So later on in the machine learning section, we'll discuss a few of those other ways to analyze your model choice. So now let's go ahead and continue with regression evaluation metrics. There are 3 general evaluation metrics for regression problems. I'm going to quickly jump back to Jupyter Notebook containing the notes for this lesson to explain these assessment criteria. Okay, so I'll go ahead and jump to Python Notebook's linear regression. And as I mentioned here, there are 3 regression evaluation metrics, right? At least 3 of the most common. There's the mean absolute error, which is the mean of the absolute value of the errors. There's the mean squared error, MSE, which is the mean of the square to errors. And then there's the root mean squared error, RMSE, which is the square root of the mean of the squared errors. So these are all fundamental variations of the difference between what you predict and actual values. So right now we can go ahead and compare these metrics. The mean absolute error, MAE, is probably the easiest to understand because it's just an average error. You take your error and get its absolute value and average. Mean square error, MSE, is a bit more popular than mean absolute error because MSE penalizes larger errors, meaning it tends to be more useful in the real world because it takes into account larger errors because it's going to square them. RMSE is even more popular than MSE because RMSE can be interpreted in Y units, meaning you can directly interpret RMSE in Y units regardless of your goal. And then these are all lost functions because, we want to minimize them. So all these values here are something that we want to minimize. We want to minimize all these errors so that we can create the best model. Make sense? So let's go ahead and go back to finish calculating out these metrics in our notebook. All right, so back in the notebook, we can calculate all of these just by saying from sklearn import metrics. And you can say metrics dot mean underscore absolute underscore error. And this will take in your Y true and Y predictions. So in this case, that's Y tests in our predictions. And you can go ahead and print it out. In this case, it is your mean absolute error. Now, similarly, you can go ahead and calculate the same thing for your mean square error. And I'm just using tab to autocomplete it here for Y test and predictions. Great. So the other thing I could also do is grab the root mean squared error. And you could easily do that just by using one of NumPy's universal functions, np.sqrt. And then move on to our previous result here. Since that was the mean squared error, it works. So if you want the root mean squared error, we just pass that in. And that gets us the root mean squared error. So what do you say, my friends? That leads us to the conclusion of the explanation of linear regression model. So to recap, we've successfully taken the data according to the futures and target, split the data into a training set and a test set. So please go ahead and come back here to train a linear model. Fit the model. Check the coefficients and intercepts to learn a little bit about the model. And then make predictions using the model and analyze our residuals. So basically, it's our model error based on the test set, and we can actually check the metrics themselves. Okay, so as I mentioned, if you want to redo this analysis in a real data set, you can. Just go ahead and explore the Boston data set that I mentioned earlier, and link to your notebook, actually. All right, my dear friend, so the next step, we're going to give you some e-commerce data, and you'll then need to create a linear regression model by following the instructions in the exercise. And then we'll go over the solutions. So I hope you enjoy linear regression, the first entry model in machine learning. All right, thanks very much, and I'll see you in the next lesson. Hello, everyone, and welcome to the Linear Regression Project Exercise Overview. So in this lesson, we're going to get a brief overview and background for the project exercise notebook related to the Linear Regression Project. If you're ready, let's go ahead and jump into the notebook right now. All right, so you can see that I'm here in the notebook, and as a quick note, you can find this Linear Regression Project exercise book under the Machine Learning Linear Regression folder. Now, you'll first notice that there are two notebooks here, Linear Regression Project and Linear Regression Project Solutions. I know some people just want to jump to the solutions, but it's all about the process. Anyway, just go ahead and try to practice before examining the solutions. You get it, right? So this is where all the code will be filled. Then you will see an e-commerce client file as well. And that's just going to be the source of our data for this project exercise. Okay, so let me go ahead and I'll give you some background for the project. All right, so picture, if you will, you've contracted with an e-commerce company based in the United States and selling online clothing, but the store also has in-store style and clothing advice sessions. So customers can go into the store, hold sessions or meetings with a personal stylist, and then go home and order their desired outfits via the mobile app or website. So the company is trying to decide whether to focus its efforts on mobile app experiences or website experiences. And they've hired you under contract to help them understand. Then you can go ahead and get started just by analyzing customer data. Oh, and another short note, we are going to be dealing with some artificially generated data. There are credit card numbers and emails, but don't worry about none of that. So in other words, it's not real, okay? So they are data, that's what's important. And go ahead, import the data, and then follow the instructions that are in bold. And if you don't want to overwrite the existing output, then you should probably keep in mind you might want to add cells. All right, next you'll do some exploratory data analysis with Seaborn by creating some of these visualizations and diagrams that attempt to understand the data. And you'll understand some questions about the data. You'll then create training and test sets for your data, train a model, and predict based on your test data. You'll then evaluate your model and also look at the residuals. And you'll be able to come up with the results. Okay, my friends? Good luck to everyone in the project exercise. Thank you, and I certainly hope you enjoy the project. Good luck. Hello to everyone, and welcome to the Linear Regression Project Exercise Solutions lesson. So in this lesson, we'll begin to examine the solutions of the linear regression project. All right, so right here, I am in Notebook, as you can see. So why don't we just go ahead and get started. First thing we will need to do is all of our imports. And so I'm going to just go in and import Pandas and NumPy. Then I will also import my visualization libraries, Matplotlib.pyplot as PLT, and Seaborn as SNS. I also need to specify %sign Matplotlib inline, and we will continue with the instructions and say import Scikit learn as we need it. All right, so then we want to get the data from the company as we will be working with the e-commerce client CSV file. All right, so it's got 4 columns. We'll go ahead and read it as a data frame called clients or customers. And we're going to say pd.read_CSV. And then we can start writing whatever we want. And if we just click on the tab, it will be auto-completed for us. Great. So let's go ahead and say customers.head. And that way we'll get to look at the top of the data frame. And of course, it's a hope of mine, I guess, that you're used to this kind of interaction with a data set by now. So we notice here that we have our email address, our membership image, and we have numerical columns such as mean session length, time spent on the app, time spent on the website link for membership, and annual amount spent. We can also scroll to the right to see them. We can also examine the describe method. That way we can get some statistical information about the numerical columns. And we can use the info method to get some basic information, such as object types, how many entries there are, how many columns there are. All right, so it looks like we have 500 rows, 8 columns. Now let's go ahead and start doing some exploratory data analysis. And remember that for the remainder of the exercise, we're only going to use the numerical data of the CSV file. So the first thing that you want to do is use Seaborn to create a joint plan to compare the time spent on the website columns and the annual amount spent columns. And this is then going to be the correlation shown that makes sense. So let's go ahead and do this. Now, if you haven't achieved the exact color, the plot should look like this story. All we can say is sns.jointplot. And we'd like to compare the time spent on the website with the annual spending amounts. So we'll go and determine that our data will be the customer data frame. And then X is going to be time spent on the website. And that makes Y free to be annual amount spent. Cool, so there it is. Now, when trying to interpret the type of scatter plot, well, there doesn't seem to be a clear trend between the time spent on a website and the annual amount spent, just by looking at it visually. So, okay, then we'll just go ahead and take a look at this later when we actually start building our model. Right now, we're going to move on and we'll do the same, but with the time spent on app column instead. So as I show you here, the time spent in app, X, and the annual amount spent, Y. Now here we should see a slightly greater relationship between time spent in app and annual amount spent. So we'll do this by saying sns.jointplot. And again, you say your data is equal to the customer. And the order of these arguments doesn't really matter as long as you specify which parameters or arguments are actually passed. So I want to say time spent on app and annual amount spent. Now remember, the specification capitalization must be exactly the same as the column name. Do you remember that too? Of course. So for instance, customer wasn't correct. So I'll need to say data equals customers. Okay, and here we have the same plot. And there's going to be some sort of relationship between increasing the time spent on app and increasing the annual amount spent. So we'll go ahead and use the joint plot to create a hex plot. And that'll compare time spent on app with the length of membership. And we can do this again with joint plot specify. X is equal to time spent app. Y is equal to length of membership columns. And then we'll specify kind as equal to hex in order to create the hex bin plot. And finally, we want to say data is equal to customers. So let's run that. And now we see the hex plot. Very cool. So let's go ahead and examine such relationships across the entire data set using the pair plot to recreate the plot below. And don't worry if you can't get those same colors. You can just say SNS point pair plot. And then pass in your customer's data frame and run it. Now, because it is a larger data set, it may take some time depending on your computer. Okay, so you should get something that looks like this. Now, based on this plot, it seems to be the most relevant feature of the annual amount spent. So, depending on whether you go ahead and look at the X or Y axis, we can look at the column annual amount spent, which is right here at the bottom. So annual amount spent, we're just looking at this visually. It looks like it could be the highest correlation right here. Seems more like a straight line. And this is the length of membership. So then the answer to this question, visually based, is the length of membership. So what we want to do now is to create a linear model plot using the Seaborn LM plot of annual amount spent versus length of membership to try to draw this relationship a little bit more clearly with some detail. And we can go ahead and say SNS.lm plot, where we want X to be the length of membership, Y is equal to annual amount spent, and data is equal to customers. And then we're going to go ahead and run this, and yeah, we've got the same plot. Now, let's notice here that there seems to be a good linear fit to this data. You may also notice this because as long as these error bars go away, there are very few errors. So we know a pretty good idea that the longer you stay a member, the higher annual spending you're going to make, which again makes sense. So now let's go ahead and generate our training and testing data. And we'll start this by specifying a variable X equal to the numerical properties of customers and a variable Y equal to the annual amount spent column. So let's take a look at our column names, saying customers.columns. And this will make it easier than writing down a lot of information, right? So I can go ahead and say Y is customers, and what we're trying to estimate is the annual amount spent. And then for X, what we want are data frames numerical columns. And that's going to be equal to mean session length, the time spent on the app, time spent on the website, length of the membership. So let's go ahead and put that in. So customers, and then take in a list of the column names, and then go ahead and put this on one line. But that should give us numerical columns. Okay, great. So we have Y data, we have X data. Y is what we're trying to predict, and X are numerical properties for it. So we'll go ahead and then use the model selection train test split from sklearn, and that'll split the data into a training and test set. And we will set the test size equal to 0.3 and the random state to 101. Okay, so you'll always do this in the machine learning section, right? So you'll pretty much memorize this eventually. But we'll say from sklearn model _ selection, and you can tab to get these options, then import train test split. And then we can go ahead and say, well, I would like to do train test split, do shift tab, and see the full documentation string. So scroll down until you come to the examples, and you'll see an example here, and go ahead and just copy and paste it. And then this kind of thing saves you a lot of typing, of course. And now you want to do a set, the size to 0.3 and random state to 101. Now you don't need to set the random set to 101, but if you want your results to match mine and your solutions notebook, you should set the random state. Otherwise, under normal circumstances, you can just leave default random state and you don't have to add this parameter. Cool. So let's go ahead and run it. I'll make sure that everything works out correctly. Okay, so now it's time to train our model with our training data. We're going to go ahead and import linear regression from sklearn.linearModel. So what we want to say is from sklearn.linearModel, and you can do tab autocomplete, import linear regression. Then we're going to create an example of a linear regression model called LM. So let's go ahead and create that object. And then LM, we want to fit all training data. And we'll do this by saying lm.fit. So here, if you do Shift-Tab, it will tell you in what order you want X and then Y. And since we are only dealing with the training data, we'll say X-train, Y-train. And go ahead and fit that. All right, so now we have our fitted trained linear regression model. We're going to print out the coefficients of the model, and we can do that just by saying lm dot and start typing coefficients. And eventually at COEF underscore, this will return the coefficients as an array. Well, let's keep guessing from our test data, shall we? Now that we have a fit model, what we can do is predict the test values and evaluate its performance. So we had to use lm.predict to predict the X test set. And we can pass in the X underscore test, then match the results to a sequence called predictions. And then we want to create a scatter plot of actual test values versus predicted values. So we can go ahead and say plt.scatter, pass in y-test, and then pass in predictions. And we can say plt dot. We'll go ahead and do some labels here. We'll say X label number is our Y test. It is true values. And plt.y label is the predicted values. And if we go ahead and run this, notice that our model is actually in pretty good condition. Now, this would mean if all points on top of each other had an absolutely perfectly straight line, we have a perfect pattern in test data. But for now, we can see a bit of error, but looking at the predicted values versus the y-test, and the fact that we only use it for numeric columns, yes, this is pretty good. Okay, so let's go ahead and actually evaluate this model, not just visually, but with a little bit of math. So now let's evaluate our model performance by calculating the sum of squares and explain the variance score, which is r squared. Now, do you remember from the previous lesson, we can do all of this just by saying from sklearn import metrics. So we can start by saying print MAE, or they are mean absolute error. Okay, so I'm going to go ahead and then call metrics.mean, in this case, mean absolute error. And we just pass in the y-test, the true values versus the production values. So let's just go ahead and copy and paste this answer. You're actually going to be using this answer quite a bit. So the same cell, I can say print MSE metrics dot, and in this case, we want mean squared error. And I was going to copy and paste y-test predictions. And then we want RMSE. So we say metrics dot. Now in this case, we want the mean squared error. And again, copy and paste. But remember, since this is the root mean squared error, we're going to go ahead and say np.sqrt and take the square root of that. Score. And then make sure this runs correctly. We got great and matching results. So now you'll notice that there is another minor issue here explained in the variance score. Now, it wasn't specifically mentioned in the bold instructions, but it was a bonus, okay, if you discovered it yourself. But what you can do is say metrics dot. And if you start typing EX and do tab autocomplete, you will also explain the variance score. And this is the R-squared value for a regression fit. And you can pass in again y-test and their predictions and see how it ran. So let's go out and check it out. We get 0.98. So if you're not familiar with our square, this is basically a measure of how much variance your model explains. And we explain 99% of the variance. You can see that we've got a very good fit model, especially in the test data. So now let's discuss residuals. So we should have gotten a very good model and a very good fit, just like we saw. So we're going to quickly explore the residuals here to make sure that everything was okay with our data. We're going to draw a histogram of the residuals and make sure that it looks normally distributed. And you can use the plt.hist or Seaborn dist plot. So we can go in and just do Seaborn and say SNS point dist plot. And we want to say y-test minus the predictions. And we'll go in and specify the bins will be slightly larger and we'll get a distribution. So it looks pretty normal. And by looking at it, what we're working on, and we already know that we already have a good fitting model, so we shouldn't really worry about the residuals. And then as a result, we still want to find the answer to the original question, which was that we focus our efforts more on mobile app or website development. Or maybe it doesn't really matter to membership. Time really matters. And we're going to see if we can interpret the coefficients at all, in fact, to get an idea. So why don't we do this? Why don't we try to recreate the state of frame below? Now we did this similar data frame, and it's going to do that. So we pass in the coefficients as our data, and we say x.columns. As the names, we'll call this CDF. We say columns is equal to coef. Now let's go back and check the CDF, and we get the same data frame. Okay, so now the question is, how do we interpret these coefficients? And there is a small reduction cell in case you want to write it here, but you don't have to think about it in your mind. Basically, the way to interpret them is the coefficients one by one. For instance, the mean session length. If you keep all of the properties constant, 1 unit increase in mean session length is associated with about $26 more in spending, right? And similarly, 1 unit increase in time spent in-app is associated with an increase of $38 spent per year. And the time spent on a website is actually shown as a 19-cent increase, which isn't that great. And the membership duration is the strongest feature here. So if you keep all the other features constant, a 1-year increase in membership duration is associated with an increase of about $61. So now the question is, should you focus on the company's mobile apps or, given that information, the website? Now, I'll give you a hint here. This is actually kind of deceptive because there are two ways to think about it. So if you look at our coefficients and the data in our model, we can develop the website to capture the mobile app. Therefore, one way to think about it is that the website needs the most work, and we should concentrate most of our efforts here. Or you could think of it the other way. That is, you have to develop the app further because this already works much better. Understand? So this sort of answer really depends on a number of different factors going on at this particular company or wherever this state is actually coming from. And you're going to want to explore the length of relationship between length of membership and app on the website before you come to a conclusion. And indeed, this is where the role of data scientists begins to blend in with the role of someone with a bit more business acumen and more familiarity with management. So, how much will it cost to develop the app compared to the website? And then, that kind of decision tree. So, in other words, all of these choices are going to have costs associated with them. And I would say that it's a little difficult to say this without expert knowledge. So what you can do is report and show this information in an informative way, but you will actually need more information about the cost of decisions to choose the right focus. But at least we now have a fully informed history in order to make this decision. You follow? Cool. So my dear friends, I hope you enjoyed this project exercise. If you need any reviews, you could, of course, browse through the solution notebook or review the lesson again. And again, the data is not real. It is indeed artificially created. So we will now begin to focus on real data sets rather than real-world problems as we move forward in the machine learning section. So thank you very much to everyone involved, and I want to see you in the next lesson.